Hi all, welcome to the lecture series on Aerospace Propulsion. Myself, Mr. Manideep Gupta, Assistant Professor from Department of Aeronautical Engineering, MLR Institute of Technology. Today the topic which we are going to discuss is about rocket principle and rocket equation. Rocket principle and rocket equation. Coming to the overview of today's presentation, we will discuss about the rocket principle, rocket equation, that is Tsiolkovsky rocket equation. And we will go through the mass ratio of the rocket. We generate equations for mass ratio of rocket. Also, we will discuss about the desirable parameters to achieve high velocities. The desirable parameters for rocket to achieve high velocities. So, coming to the rocket principle. So, rocket principle, everybody knows that there is an equal, for every action there is equal and opposite reaction. And that action is being generated by the momentum of gases. The action means nothing but the gases are coming out. Because of that reaction, the rocket is moving on opposite direction. But how this action is being generated? This action is being generated with the help of chemical reactions who are sending high velocity gases out. That is nothing but the action. For that there is a reaction, that is the rocket moving upward. Okay, that is the basic principle of rocket. So now we are going to find the equation. Suppose if you see the diagram here, there is a person. Okay, there is a person, stationary observer, who is in the inertial frame of reference. Okay, and this is a case 1 and this is case 2. That means second case. This case 1 is at time t. Okay, and this is the case 2 at time t plus delta t. After a small duration of delta t, this is the position of the rocket. So at the time t, the mass of the rocket is capital M and the velocity of the rocket at time t is given by capital V. At time t, not at the initial or not at the exit, at the end. This is the parameters at the time t. Okay, time t, the mass of the rocket is M and velocity of the rocket is capital V. And the exhaust efflux velocity is Vj. Efflux velocity is Vj and the mass flow rate of the gases is m dot. Okay, and next this case 2, this is a rocket at time t plus delta t. You can see the mass of the rocket at time t plus delta t is m minus delta m, because some mass of the gases propellant is consumed duration of time delta t. Duration of time delta t, some propellant mass, that is delta m, is being consumed and it is ejected out of the rocket. It is ejected out of the rocket. So the mass of the rocket will reduce from m to m minus delta m during a time delta t because of this delta m ejection. And because of this delta m ejected out, the rocket will gain some velocity. So that velocity gained by the rocket is given as delta v. So what happens? During this time delta t, the rocket velocity has increased from v to v plus delta v. It has increased from v to v plus delta v. So now what we are doing is, we are going to calculate the total velocity gained by the rocket. How much velocity the rocket is going to gain from initial to the exit, end of the operation. So that is what our purpose here. So consider traveling time, traveling at time t, the rocket is traveling at time t and the velocity of the rocket at time t is capital V. And next the mass of the rocket at any time t is given by m, the mass of the rocket at time t. And next the rocket exhausts, okay, the rocket ejects out mass at constant rate. The rocket ejects out mass at constant rate, that is m dot. Okay, then if this rocket is ejecting mass with rate m dot and let us say this delta m is a mass ejected during a time delta t, then I can write this delta m. Delta m is equal to m dot into delta t. M dot is the mass flow rate of the gases, that is in kg per second, and delta t is in terms of seconds. So I want to calculate the total mass ejected. So if I multiply this, second will get cancelled, I will get the mass of the propellant ejected out. So delta m is equal to m dot into delta t. Next, Vj. Vj is the velocity at which the delta m is ejected. Okay, delta m is ejected with velocity Vj. Okay, and this Vj is relative to the rocket. Whatever the velocity Vj we are considering here, flux velocity, that is with respect to the rocket. Okay, and if I want to calculate this Vj with respect to this inertial frame of reference, it will be different. So it will be what happens, V minus. So already rocket is moving in the forward direction with velocity V, and Vj is in opposite direction. So the velocity of this velocity of this delta m with respect to this inertial person will be V minus Vj. Rocket is moving with velocity V, and delta m is moving with velocity Vj with respect to rocket. Final velocity, the total velocity of the delta m with respect to the stationary person is V minus Vj. Okay. Now we are going to calculate the momentum of the rocket at time t and also at time t plus delta t, and we are going to equate conservation of momentum. We are going to apply the conservation of momentum principle here. So at the momentum of the rocket at time t is given as mass into velocity of the rocket at time t. So mass of the rocket is m and velocity of the rocket is capital V. So momentum is equal to capital M into V. The same way, momentum of the rocket at time t plus delta t is equal to mass of the rocket at time t plus delta t and velocity of the rocket. So mass of the rocket is how much at t plus delta t? M minus delta m. So mass m minus delta m, and velocity of the rocket is v plus delta v. V plus delta v. Next, the momentum of the gas mass which is ejected out. Whatever the gases which are ejected out. Okay. So the velocity of the gases which are leaving the nozzle with respect to a stationary person. So what is that? Velocity of the rocket. Okay. V, right? V plus delta V is the velocity of the rocket minus Vj. Minus Vj. So this is the velocity of the exhaust gases with respect to a stationary person. So if I write that equation, so this is delta m into V plus delta V minus Vj. This is the momentum of the ejected gases. Next, now I am going to apply the conservation of momentum at time t and at time t plus delta t. So at time t the momentum is mv, here written on the left side. At time t plus delta t, momentum of the rocket we have to consider, and also momentum of the gases which are left to the rocket. I have to consider the momentum of these two. Then it will be m minus delta m into v plus delta v here, and this is the momentum of the gases. So now I want to simplify this equation. On simplification, I can write this equation. As m into delta v minus delta m Vj equal to 0. M into delta v minus delta m into Vj equal to 0. And further, if I write the equation for velocity gained by the rocket, that is delta v, then it will become delta m by m into Vj. Delta m by m into Vj. So delta v is equal to delta m by m into Vj. This is the velocity gained by the rocket during a duration of delta t. Okay, in a time of delta t, the velocity gained by the rocket is delta v. Suppose if I want to calculate the total velocity gained by the rocket from initial to the end, then I have to integrate this. Okay. So consider the initial mass of the rocket is mi. Okay. Consider the initial mass of the rocket is mi. And at that case, if I want to calculate the mass at particular instant, mass at a particular time, then the initial mass minus mass of the propellant consumed. Mass of the propellant consumed is m dot into t. So mi minus m dot, mass total of the propellant into time t. So this is the mass of the propellant ejected out, and this is the initial mass. So if I do this, then I will get the final mass of the rocket at particular time t. So m is equal to mi minus m dot into T. And the propellant, mass of the propellant ejected during the duration of delta T is m dot into delta T. Now, I will substitute this 2 here. Next, I will substitute this 2 here. Then I will get this equation is equal to delta V is equal to Vj m dot delta T by mi minus m dot T. Okay. If I integrate this from time T is equal to 0, when the rocket has initial mass mi and the stationary and the final time is Tf. I am integrating from T is equal to 0 to F. T is equal to 0 to F. So, when the final mass, what is the final mass? The final mass of the rocket. The final mass of the rocket. Okay, the rocket is burned for a duration of Tf, then initial mass minus propellant burned out during a time Tf. So, this is the equation for final mass. Mf is equal to mi minus m dot Tf. Then the velocity gained is delta V. If I know the delta V, then we will get this delta V as delta V is equal to integration from 0 to Tf into delta V. Delta V equation we know. So, if I substitute delta V as Vj m dot dt by mi minus m dot T, then I will get delta V is equal to minus Vj log mi minus m dot T from 0 to Tf. So, if I substitute Tf at the Tf is the final and 0 is the initial, T is equal to 0, right. So, then this equation will become minus Vj as it is log mf by mi. So, what is this? If I substitute Tf here, this term will become mi minus m dot into Tf. What is this? This is mf. And next, if I substitute T is equal to 0, then this equation will become mi minus m dot into 0. So, that is nothing but mi. So, finally, it will become mf by mi. So, Vj, it can be written as the ideal velocity increment delta V can be written as delta V is equal to Vj log mi by mf. If I send this minus into this, then it will become mi by mf. So, I have written this. Then finally, delta V is equal to Vj log mi by mf. This is nothing but called as the Tsiolkovsky rocket equation. Next is mass ratio of the rocket. Mass ratio of rocket. So, the ratio of the final mass of the rocket. Ratio of the final mass of the rocket after all the propellant has been consumed, mf, to the initial mass of the rocket before the operation, that is mi, is called mass ratio Rm. Okay, Rm is equal to mi by mf. Mi by final mass to initial mass. And next, the final mass of the rocket can be written as in terms of three different parameters. One is payload mass mu and structural mass. So, if I take the initial mass of the rocket mi, it will have structural mass ms, it will have payload mass mu, and also it will have propellant mass mp. This is how I can divide the total mass of the rocket into into different segments. One is structural mass of the rocket, payload mass of the rocket, and propellant mass. So, at the end of the operation of rocket, whatever this propellant, all this propellant will be sent out. So, this is only structural mass and payload mass will be left in the rocket. So, that's why I can written the final mass mf is equal to payload mass plus structural mass, and the initial mass mi of the rocket is equal to payload mass plus structural mass plus propellant mass. Okay, if I substitute this in the velocity increment, okay, that is what delta V is equal to Vj ln mi by mf. So, what is mi? This is mi in the numerator and this is mf in the denominator. Then I will get this equation. Delta V is equal to Vj log initial mass mu plus ms plus mp divided by final mass of the rocket, that is mu plus ms. And here we can write this term in terms of payload fraction, payload mass fraction, structural mass fraction and propellant mass fraction. Okay, alpha is nothing but alpha, we consider alpha as payload mass fraction, that is payload mass mu divided by initial mass with respect to the initial mass. Structural mass beta, beta is structural mass of the rocket ms with respect to the initial mass. The same way propellant mass fraction also, here you can see gamma, propellant mass fraction can be written as mass of the propellant with respect to the initial mass. So if I write this propellant mass fractions as alpha, beta and gamma, that is mu by mi as alpha, mass of the structure with respect to initial as beta and mass of the propellant with respect to initial mass of the rocket as gamma, then I can write this as alpha plus beta plus gamma. Okay, if I do alpha plus beta plus gamma, then it will become 1 and I can substitute this. Okay, if I want to write this equation, if I want to write this equation in terms of mass fractions, mass ratios, mass fraction, then I can write this equation as delta V is equal to Vj log alpha plus beta plus gamma divided by alpha plus beta. And this can be also written as Vj log 1 by alpha plus beta. Next, so if I further analyze this equation, delta V is equal to Vj log 1 by alpha plus beta, we can write. Okay, so if I rewrite this equation, as 1 by alpha plus beta is equal to e power delta V by Vj. Okay, so the payload mass fraction can therefore be written as, this alpha can be written as, from this equation I can write alpha as e power minus delta V by Vj minus beta. So what happens from this equation, what we can observe is the payload mass fraction alpha is seen from the above equation to decrease as delta V by Vj increases. As the value of this delta V by Vj value increases, this payload mass fraction decreases. Okay, so finally what we can see, in order to achieve higher velocities, in order to get higher velocities of the payload mass fraction, alpha and Vj needs to be large and beta needs to be small. This Vj should be large and beta should be small to get higher velocities, because beta is in the denominator and Vj is increasing the value of delta V. So we need Vj needs to be large and beta needs to be small to get higher velocities. These are the desirable parameters to achieve high velocities. So and here you can also see the trend of variation of delta V by Vj with respect alpha with respect to delta V by Vj. As delta V by Vj is increasing here, you can see alpha, payload mass fraction, is decreasing. Payload mass fraction in the sense the payload mass is less when compared to the initial mass. So we can carry less payload as delta V by Vj increases for different structural mass fractions. And the next thing is, if you consider, suppose if you consider a rocket with a small propellant mass fraction, the propellant mass is very, very small when compared to the other mass like structural mass and payload mass. If I consider like that, then what is the payload mass, the propellant mass fraction is gamma. So gamma by alpha plus beta is very, very less. Then I can written as gamma by alpha plus beta as less than 1. Okay, in that case the ideal velocity increment given by the equation, okay, ideal velocity equation can become delta V equal to Vj log 1 plus gamma by alpha plus beta, and we know gamma by alpha plus beta is very less. So finally what happened, the incremental velocity can therefore be written as gamma by alpha plus beta as delta V is equal to Vj as it is, and this log 1 plus gamma by alpha plus beta, because log value is less, then we can replace log and directly return the term, then it will become Vj into gamma by alpha plus beta, since gamma by alpha plus beta is less than 1. And finally what happens, delta V is approximately, not exactly, it is approximately equal to Vj into mass of the propellant to the final mass mf, mp by emf. This is only for condition small propellant mass fraction. So this is about the coming to the summary of today's lecture. We have gone through the rocket principle, we have gone through the rocket equation, Civil Koski rocket equation, we generated equations, we have gone through the equations of mass ratio of the rocket, and also we have analyzed the desirable parameters to achieve high velocities. Thank you.